Right on time. Okay, how many of you are new? Okay. Okay. You might want to check with me after class just to make sure that we get you up to speed. First question, including the new ones, how new are you?
Well, I'm going to audit.
Oh, you're going to audit. Okay. And when did you start? When did you get registered?
Well, registration was tomorrow.
Okay. And Diana, I'll talk to you. Has everybody done the honor code quiz? You have. You have not. You have not. Okay, you need to do that by Friday. Otherwise, they'll push the eject button and you'll go away. Okay, very good. I knew that getting started the first, there it is. Getting going the first week is hectic for you, I know, and hectic for me as well. I've taught this class for about 5 years, and all previous versions were 2 days a week for an hour and 15 minutes. And so we have a lot more flexibility in terms of timing. And I knew the first week would be intense, and I think it was. Many of you sent me emails about that. But I think we're kind of up and running. So what I want to do tonight to start is to get you going. Those of you who are new, as soon as your registration comes through, you'll have access to this course on D2L. And there is a welcome page with a whole list of things for you to do. The course is divided into 9 instructional units over the 15 weeks. And we do about 1 a week until we get into about the 6th or 7th week. And then it kind of, instruction units kind of spread out over a couple of weeks. So you're a week behind. And make sure you give me your names at the end of the class so that I can make sure to extend the assignments for you, because the assignments that have been due are already closed. So I need to extend them for you. So check with me after class, and I'll get your information to allow you to be able to do that. Okay. I want to begin, and probably take us, we'll probably spend a good hour, maybe, or more, on R. Question. Anyone not have R installed and running? Finally got you going. Everyone has R up and running and going? Okay, good. Okay, I want to, how many of you, or any of you have any prior experience with R? None. And I did ask last time, but I've forgotten who raised their hands and who didn't. Have any programming experience with programming? Even a little bit's better than none. Okay, so most of you, that's a good thing. Okay, I'm going to, give me just a moment here. We need that. And I need that. I need that. And that. Okay, when RStudio, when you get R installed first and then RStudio, your desktop should look roughly like that. And was it Jesse Tools, was it? Or, yeah, Tools. Which one? No, I'm trying to make it global options. Okay, that should make things a little bit larger for you to be able to see. When you launch R, it's going to look like this your first time out. But what I'm going to do, and you will need to do this, so we're going to create a new file. So we can just click File, and Open. Oh, I don't want to do that. I want to do File, New, and R script, a new R script file. When you do that, then your desktop and ever after will look like this. Now, there are 4 panes. Upper left up here is the script window where you can type in commands, and we'll be doing a bunch of that tonight, and I'll show you how to do that. Whenever you type a command here, however, it does not get executed until you specifically take an action to run it. You can do that by clicking this run button, or you can just do Control Enter, and it will run. So, for example, and I'm going to do something here, so let me just call this D. So I'm going to assign some stuff into the variable called D. And I'm going to use the assignment operator. It says D gets this, and I'll use the phrase gets when I type that. Now, technically, you can type an equal sign here, say D is equal to some value, but I prefer to use this and use the equal sign in other places that will be a lot more obvious where equal sign has to be used. It seems like a little bit of an inconvenience because you have to do a shift and there's 2 keystrokes to do it. An equal sign is just 1 keystroke without a shift, but you'll get used to it and it will be a good thing. So what I'm going to do is I'm going to assign to D the values, the consecutive integers from 1 to 10. And this is a little function that R has with a colon. It will then give you consecutive values between the start and the ending value. Now, if I hit enter, it just goes to the next line. So I can tell it I want to look at D. I'm going to look at what's in D. And then I'm going to look at something that we call the structure of D. The structure of D is the format or the type of variable that D is. Now, I can highlight all of these commands all together, and then do a shift enter and magically delete them. Control Z to bring them back. I'm sorry, it should be Control Enter, but I have to highlight them all. Control Enter, and it will execute those values. Now, 2 or 3 things happened. Number 1, the commands that are executed are duplicated down in this bottom window called the console window or the output window. I'll use both phrases when I communicate to you, and in the text material it will say the console window or in the output window. The results of those commands will run there automatically. And so it made this assignment. When it did this, nothing happened that you would see. There's no result here. And then I asked it to show me D, and it said, okay, here is D. Those are the numbers 1 through 10. And then I asked for the structure. Oop, it didn't like that. It gave me an error because I made an error. So I have to do structure, parenthesis, D, parenthesis. Now, if I just want to run that command, I just leave the cursor there, do a Control-Enter. And now it says that the structure of this guy, it is an integer, and these are the values, 1 through 10. Okay? R has a number of data types and formats, and they are nicely outlined for you in R in Action. I told you you did not have to buy this, and you don't, but if you do, it would be a good idea. But I did find a link to a PDF version of this that you can download, and that link is on the course website under, where did I put it? I don't remember now. Let me see if I can't launch a browser and... Let me see if I can go find it real quick. Okay, under content, while I'm here, there's a couple of things. In this module called Supplemental Readings and Materials, are in action right here. If you click that guy, it'll go to a link and download the PDF version of this whole thing, and then you'll have it. Then you'll have to save it to keep access available to it. In addition, there is LOL cat functions all. I need to update this with stuff that happened over the summer, but it will get us through for the intermediate period of time. And this is a little 5-page document, and I'm a paper and pencil guy, so I make copies of everything and then I just carry them around with me, but it has all of the LOL cat functions that we're going to use. And it does, R will allow you to do anything you want on your own, but rather than have you try to figure out how to do everything on your own, we're going to use this little package called LOL cat that has built-in functions that do the things that we need to have done in almost all cases. So when you get that thing, it will have items listed by instructional unit. And so from the first row down to right here are all of the functions that we're going to use that are in LOLCat for instructional unit number 2. The priority of use, I've got here one, sort of, there's something right here that says 2. For any priority of use item that has a 2, we're probably not going to use that at all. We don't have to do anything in LOLCat for Unit 3, but starting in Unit 4, we do quite a bit. And then in nothing in Unit 5, a little bit new in 6, a bunch new in 7, and 8 and 9 is where the lion's share of all of this is going to be. That's where we really get down to doing statistics. Up until that point in time, it's just laying the foundation. Off to the right-hand side here, I have the actual commands and how to, what to do. You don't type in the R. I'll show you a couple of these as we get going. So it's probably a good idea for you to make a copy of that and have it available. If you're the kind of person that can take your small screen on your laptop and split it in half and do your work over here and have reference stuff over there, then that's fine with me. Do it whatever is easy for you. I'm not your dad, even though I'll sound like I'm trying to be your dad from time to time. Just ignore me, just like you did your own real father, and then just do what you want anyway. Okay, so we'll go through all of these kinds of things as we get going. Okay, so now, so we have an integer here. Now, I'm going to show you some interesting little stuff. By the way, if you're down here in the bottom left-hand window, it's called the console window. Anything you type in will occur automatically. It will execute that one command by itself. That's the nice thing about RStudio, is it lets you build a series of commands and then execute them all at once. And you can test them as you go and change and fix them. For example, up here, there is a very special, nice little function in R that if you surround a command with parentheses, as I have just done, what that does is it says, do the operation that's inside and then print the result. Print the result. So let's go down here, and I'm going to get some space. Now I'm going to go back up here and simply take that one line. I don't have to highlight it. I can just click anywhere on it and do Control-Enter. And it will make that assignment and then display the result. And I will use that quite often in class. I've tried not to do that for the material that's in the text because it doesn't help much to do that. When you execute the results, they'll come anyway, but you will see that. Now, in R, there are a number of types of data. There is no such thing as a scalar or a single value in R by a unique name. The lowest level values is a vector. There's a string of numeric values. That vector can be numeric. It can be logical, that is yes, no, true, false. It can be character data as well. And so it's a good idea to ask R what the nature of that variable happens to be. And we do that with the str command. So I ask, what is the structure of D? And it said, well, it's an integer with 10 values. So now I know it's an integer, but I'm going to do something up here. Now I'm going to say, let me take D dot factor. Variable names cannot have spaces in them. You are permitted to use a period, which is very, very common in R. Or you can use camel caps, that is capitalizing the first letter of certain words along the way. I tend to do that a lot myself because I just like it. So this guy, D factor, I'm going to, that value, that variable gets as factor. So now this is a command. So it's going to take what comes next and turn it into a factor and sign it into D factor. So what am I going to make into a factor? Well, D. I have the numbers 1 through 10, and I'm going to convert that into a factor with this command, Control-Enter. And now you see it doesn't look like anything happened. Down at the bottom screen, you can see that it executed that command. It says, okay, I did that, and I don't have anything to show me. You told me to put this over here, and I did. Now, if we want to see what's in there, then we could have done it by simply typing D factor right now, like that, and it will give us that guy. Or, let me get rid of that. I could have simply put parentheses around this, end, where's it, end? And executed that, and it would have made the assignment, and it would have also printed the results. So I tend to use that quite a lot because when I'm doing stuff, when I make an assignment, I want to make sure that it got done, and so I look at the results. Now I want to find out what kind of a variable is D period factor. Well, we said to make it a factor, let's see if it really did that. So we use the command str, D dot factor. See, and nothing happens unless you do Control Enter. And it says now this guy is a factor with these levels. Now, when I printed out this guy right here, it gave me the values 1 through 10, right? So, normal person would think that you could calculate the mean of those values. So let me tell it to compute the mean. The mean of, you have to spell it right. Computer is a cruel taskmaster. If you make any mistakes, it doesn't let you skate. So I want to compute the mean of the variable d, which it said was an integer. Integer is a numeric value, and so when I tell it to do that, it will execute that command. Now notice, if I wanted to save that command, I would have to enter it up here in order to save it. So when I type it down there, it just simply executed it. Now, let's do something here. Mean D. Now, if I do a semicolon, I can put an additional command on the same line. It will do multiple commands on the same line. I typically don't do that. Sometimes for convenience I will, but generally speaking, no. So now I'm going to tell it I want to compute the mean of the values in D factor. Okay? And I'm going to, since I don't trust that, I'm going to highlight the whole line. And just to show you, I click Run, and it will run that command. Now notice the first thing it did is it computed the mean and gave me 5.5. And then it said the other one, warning, can't do this. The argument is not numeric or logical. So it says I can't calculate the mean of a factor. Now, ladies and gentlemen, for you and I, a factor is a categorical variable. When we go down our types of data, we come down on the right-hand side, we have continuous, left-hand side, we have discrete. Then discrete is broken into ordinal and nominal. In that nominal area, we said that we're going to call that categorical. When you have a factor, it's categorical variable, even though the contents are the numbers 1 through 10. Those numbers are actually characters, they're not numeric values. Okay? And that's very important. Computer makes a big distinction between a 1 that is treated as a character as opposed to a 1 that is treated as a number. Okay? So those people who read phone numbers and say, my number is 303, well, it's really not 303, it's 303. Now, I'll be a stickler about trying to do those kinds of things because when I was in the military, I was in the artillery, and they didn't tolerate using letters for numbers for obvious reasons. Okay, so if your variable is not numeric, you cannot do numeric calculations on it. Now, for us, when we bring things in most cases, it's going to be just fine when the data comes in from a file and R interprets it. It will treat numeric values that are in the data file as either an integer or as numeric. If it sees decimal places, it will definitely call it numeric. If it sees integer values, regardless of their magnitude, if there's no decimal values, it could call it numeric or integer. But if there are other characters in there, correct me if I'm wrong, Jesse, if I have a data file that has numeric values with commas, it will treat that as factor as opposed to reading the commas. Well, let's find out. Cool thing about R is you can figure out anything. So I have a number is going to get this. Now, by the way, this is a magic function in R. The C function, it means combine or put together. This thing you will see all over the place because it allows you to take a number of different items separated by a comma and treat them as if it were a single item, and R will decipher it. When it sees the C, it will decipher it and recognize that there's pieces in there. And it's really, really handy. So what was I going to do? I was going to give this guy one. Oh, yeah, see, it won't even let me do this. Because if I put 1 comma for what, 1200? And then let's say I wanted 1536, comma, and a number like 2122. When I do that, there's commas. Every time it sees a comma, it starts over again. So it's not going, what it's going to do is it's going to store in n. Well, let's look to see what it stores. So let's execute that command. And then display n. Oop. Oh, there it is. So it thinks n has the contents of 1, 200, 1, 536, 2, 122. Okay? Now here's another little interesting little function in R. To find out how many values there are in a variable, which is a vector that only has one score in it is a scalar, but R calls it a vector of length 1. So the number of items in there is called the length. You and I are going to learn to call that the sample size, n. So we want to count the number of values in there. I can tell it, give me the length of n. Okay? And it says there's 6 values in there. And I says, well, why are there 6 values in there? I only wanted 3 values. I wanted 1, 2, 3 values. And it says, sorry, you used a comma, so I'm not going to let you do that. Now, when you have extra characters other than periods and plus or minus signs in numeric values for yourself, you got to be careful, because if R thinks that it's a character, it will treat everything in that variable as character data. And if it's character data, as you saw, it won't calculate statistics on it. That's the problem you had. Okay? So I'm just giving you a whole little batch of simple little commands here. And you can always try things out in R and see what's up. Okay, so the length gives you the number of items in the variable that you put in there. So now all of these commands are actually functions. So there's an action, and then the action is taken on the things that are inside the parentheses. Now, the interesting thing about R is you can wrap these things around each other. You can keep doing more and more and more and more, and putting functions inside of functions inside of functions inside of functions. So, for example, if I take n, I can find the median. Now, this is going to be an interesting value. One thing that you should have learned from reading this content, the median is the value in a set of data that is what? What's the median? The middlemost number, the one that's in the middle. Okay? Now, this is interesting. If you have an odd number of values like 5, it's exactly the guy in the middle. So if you count from either end, 1, 2, 3, 4, 5, 1, 2, 3, it's the same guy no matter counting from either end. Now, what if you only have even number? Then it's the average of the two guys in the middle. We want the score that's halfway between, halfway in. So 1, 2, 3. So halfway would be 2.5, 1, 2, 2.5, same no matter which end you go from, okay? So now, given the way that these numbers are, when I ask it to calculate the median of n, let's look at the data values. We've got, the data values are 1, 1, and 2, and then 200, or 121, 122, 200, and 536. So the median is going to be what? Halfway between 2 and 122. 62. Okay. And whenever you do calculations, you need to look at the results and ask yourself a simple question. Does this make any sense? Pardon? It sorts it itself. If I want to sort it, I just tell it to sort. Now, some commands will give you a result without you putting parentheses around them. If you execute a command and it doesn't show you the result, then just put the parenthesis around it, and it will give you the result. Okay? Question?
So I'm unclear on why you put the C in front of the vector of numbers.
That tells it to combine those values all together and assign it to this vector. I've always done it that way. I'm not so. Let's call this
Probably could have bracketed it then and left the C off or something.
number 2. Let's say we go now, let me execute both of those. See, it doesn't like it. If I go back up here and put parentheses around it,
Function.
highlight both, Control Enter, it doesn't like it. So by putting the C in front of that value, it tells it to combine or concatenate those things all together. It's just one of the things that R does that is actually really cool, but something that is required.
Make it as an array.
Yeah.
Okay.
To make this value as
Yeah.
array.
It makes it into an array.
Yeah, and it creates it as and an array is a multi-dimensional representation of data, and basically a vector is a one-dimensional array, and then a matrix is a two-dimensional array, and then R has another data type which is actually called an array. Okay, and so you'll see those kinds of things going on. Okay, there's a whole bunch of this kind of stuff that I wanted to talk about. Again, any command that you run up here, you can save. If you don't want those anymore, you can say, I don't want those. I'm just going to get rid of them. You get rid of them. If you execute something down here, it executes, and it doesn't save anything for you. So get in the habit of doing this. What I did for this whole last semester, and last semester was the first time I taught R. I am not the world's greatest R programmer by a long shot, right, Jesse? He is way better at it than I. He's been using it for a lot longer, and he's taught some intro stat classes across campus using R. So if you have R problems, send them to him, and you'll get correct answers back. You'll get correct answers back. Eric, you had a question. Is it Nick? Nick.
If I have raw data in an array that's not ordered, will sort order it as
Yes.
a function?
Yes. And there's also another command called order, and one of them works on the values, and one of them works on the index values, and so you sometimes have to play with those things. Okay, now in our little example here, in Unit 2, we started by describing some things. This paragraph right here, very, very important. The big 5, anytime you have data that you're going to begin the analysis, doesn't matter how complicated it is, you always want to begin with a descriptive summary of the data. And that's why Chapter 2 is after the intro stuff. Then we start out descriptive. The title here is Descriptive Methods, an introduction to them. When we describe our data, we're trying to see what's there and get a picture and a numeric representation of it. It's highlighted in there or bold-faced. We never look at numbers without looking at pictures. And we never look at pictures without also looking at numbers. If you try to do one on only one, I guarantee you'll make a lot of mistakes that you shouldn't make. Look at pictures and numbers. And from then it says, by the way, when we have data that we're trying to understand from the outset, there's 5 things minimally that we always want to know about our data. Number 1, we want to know about the center, the middle value. And we will learn as we go to call that the location. Think of the number line. You have a number line, and you have all of your data, and the numbers are spread out along that number line, and somewhere in the middle of the batch of your data is the center. Now that center can be represented in one of three major ways: the mean, the mode, and the median. The mean is the arithmetic average. The median is the middlemost value by position, not value. And the mode is the most frequently occurring score. The mean and the median are a calculation. The mode is done by observation. Okay? You have to create some kind of a frequency representation to do that. So we want to know the center. Center tells us about the most common, or what is, quote, common, or what is typical. And we use the average as the word to describe it. Now, in some statistical contexts, the word average means the mean. That is, you add, when you were in elementary school or secondary school and you learned a little teeny bit about statistics, the teacher taught you the average. Or you want to know what's the class average. Well, you add up all the scores and divide by the number of scores. That gives you the average. We call that the mean. Technically, the median and the mode are also, quote, averages. They're just not the arithmetic average. So we will use the terms mean, mode, and median. Okay? Then we also need to know, oh, this is kind of cool. I know it's a sidebar discussion. I went with my wife to Walmart last night. And was walking down the aisle, and I came around the corner, and there was a woman that was 7 feet tall. And I kind of glanced at her and tried not to make a spectacle, so I just kind of went on my business, turned the corner. There was another one, 7 feet tall. What's going on in your mind?
Sisters?
What's that?
They were family?
Were they sisters? Were they twins? Were they the same family? No. One was white and one was black. What?
Ball team.
Maybe it was a female basketball team. Okay? All right, now let's look, since we made basketball, and the reason that you were kind of wondering about that is because it is what? A very unusual event. Based on what we know as is typical or common in terms of the heights of females, 7 foot is one that's not common. It's very different from the others. So not only do we want to know about common, we want to know about variability or dispersion. Basketball teams have 5 members. Okay, in your mind, think of this. There is a team, Team A, they're going to play Team B. Team A has people 6 foot, 6 foot, 6 foot, 6 foot, 6 foot. Okay. The other team has 7 foot, 6 foot 6, 6 foot, 5 foot 6, 5 foot. Now, they both have the same average height. Which team is likely to win?
Well, I mean, it depends. Like, is the tallest person the center?
Yeah.
Okay.
Yeah, you can let these players play any place you want them to play. And so probably the tall one would be the center, right? And just throw it to the big person. And the person just puts it in. And now what about the 5 foot tall person? Well, we hope that they're really fast and quick, right? So they can sneak in underneath the arms of those big guys, snatch the ball, and give it to the big person, right? Okay, so you learn something about these two teams. If I told you we had 2 teams that had the same average height, doesn't tell you everything you might want to know. How different are they? So a measure of dispersion or differences, we call it a measure of spread, center and spread. How much do the values spread themselves out? Okay. Now, center and spread typically refer to continuous variables, although they can refer to ordinal type data or even nominal categorical data. So, there's not enough differences here. Normally in a class, I can point based on the color of hair and say, okay, this is a 1, this is a 1, this is a 2, this is a 1, this is a 2, this is a 1, this is a 2, a 1, 1, 3, 3, 4, 5, and then 56. 56 is one of every color possible. And then ask, what do those numbers represent? Well, they represent categories. Well, if I'm interested in looking at a categorical variable and I want to know the most common, what do I use? What? The mode. The average makes no sense, does it? By category. And the median doesn't even make any sense. See? So you're already beginning to understand the nasty, nasty stuff that we've been tortured with for the past week, measurement scales. Okay? So you have to use the mode. The mode is a measure of what is most typical or the most common, the most frequently occurring value. And that's the only value that's appropriate for categorical kind of data. Now, dispersion, there's a variety of different measures of dispersion. You read about them. We have the variance and the standard deviation. They're the most common, the heavy lifters of statistics for continuous data. And there's a little thing I'm going to do here on the screen in just a moment. Then there's also data types dictate that we can't use that, we have to use something else. When we look at data that's based on the order, then we can identify what I call the aisles, I-L-E, apostrophe S, the aisles. So we have percentiles, quartiles, deciles, which we don't normally use, but we could, the aisles. They're measures of position. And when you have ordinal data, that's what you have to use is position, not the magnitude. So I can talk about the score that cuts off the bottom 25%. That is the first quartile, the 25th percentile. Then I could go up and pass up 25% more, and I get to the middle, which is the what? The median. And that lives at which quartile? The second quartile. And then if I go 25% more, I come to the third quartile. And then above that, there's 75% below, 25% above. So now, based on the ordinal position of values, I can give you the spread across the entire distribution. That's called the range. Now, range is okay, except for sometimes data has one value that's weird, or two values that are weird. And weird values are either going to be really high or really small. And if you calculate the range based on them, the range is going to be unduly influenced by a single value. So when we have data that is weird relative to the rest of the data, which have a name called outliers, by the way, we may want to use some other measure that's not so sensitive to them and look at the spread across the middle half of the distribution, which is called the what? Somebody knows. Oh, she's thinking. It's coming.
I was close, but I remember there was a question on this.
She closed her eyes, but she didn't grunt hard enough. You have to close your eyes and go, oh, then it'll come to you. What is it?
Interquartile
It's
range?
the interquartile range.
Oh, I knew it.
The interquartile range. It's the spread across the middle half of the data. Okay? Now, that's a good measure of spread. Now, you could look at the spread across the middle 90% by going from the 5th percentile to the 95th percentile. And then if there's any outliers beyond that, then they won't be bugging us. So we can do that, but that's very, very commonly used the interquartile range. But that's what we'd use for ordinal data and data that doesn't have any weird, or that has weird guys in there. We can kind of minimize their influence. We don't throw them away. We can say, okay, you're the first one, you're the second one, third, up to here. Then we go from here to here. And then we've got it. Now, the software will calculate all of these values, interquartile range, the standard deviation, the variance. Now, when we have categorical data, we typically simply define the frequencies of each of the categories in order to understand spread. The modal category is the one that is most representative, but then the differences, we would say, if I ask you about, if we looked in the, for this class, if we went around the room and asked you to indicate your religious preference, and we put them in categories. However, we decided to identify them. Okay, if we just say Christian or non-Christian, then the data is what kind? It's binary, dichotomous. Okay, now I could add other categories, so I could say Christian versus Jewish versus Muslim and Hindu and Buddhist, and I could start to name a number. Let's say that I had those 5. And then one of the things that's always done is we always add another category called other, just in case we don't catch everything. And researchers sometimes have an interest only in these things, but they want to know about others involved, and so they'll put a category like that. It's not that they're dissing them; they're just saying I don't have any particular interest necessarily in anything other than these. Okay, but you'll find out when we get into probability that having this other category is really a valuable and a useful one because it completes the set. So that every item in our data set belongs in a bucket, in a category, okay? So we can do that. Now, if I took that for this class, and then I said, okay, let's go to the registrar's office and have the registrar do a computer dump by listing of all of the different categories that students have identified as their religious preference. Would there be more than the 5 categories that I just talked about? In all likelihood, yes. Okay. So when I talk about and I want to understand how much dispersion, how much difference there is among those categories, I can't use a numeric value like 5 or 10 or 18. I have to know each of the individual categories and the frequencies with which they occur. And then in order to truly understand the dispersion, the differences, okay, I'm purposely avoiding the word diversity because diversity has surplus meaning that I don't want to contaminate what we're trying to learn in terms of statistics. But in fact, it's an index of dispersion of diversity. So we'd have the number of categories would be an index of diversity, for example. If everyone going to the school had just one religious preference, then there's not a lot of, quote, religious diversity. There's not a lot of dispersion or difference. Okay, so it kind of fits in, but I try to avoid using politically charged words so that we can zero right in on the concept. So when we have nominal data, then the standard deviation or the interquartile range doesn't make any sense. So that's why we begin to learn about these categories, the types of data, because it tells us the kind of statistics to use. And then once we have statistics, if I told you that I had something and the average was 10, and you try to refer that back, and I tell you what the characteristic of interest is, and if it's a categorical variable, then you know right away the average isn't going to tell you anything. So that's why these things are so important. So I'm trying to tie together the stuff that at the beginning is, I understand that it's kind of awkward and confusing and about okay, we have all these identical parts that are in a big box, and we're interested in the number of them, and we weigh them. But we're gonna tear out or remove the weight of the box. That's ratio scale data. Weight is a continuous variable. I'm interested in the count, which has it's a discrete variable, but it has ratio properties. And when I'm not weighing the box, if I'm weighing the box, then I have that automatically, that converts it to interval scale. Anytime you're adding or subtracting a constant, you go from ratio to interval. That's going to haunt you. Just make a note. That's going to haunt you as we go through up through the first exam. After that, it gets pretty straightforward. We're going to talk about things like whether the package is there or not, whether we're at a 0 point or an offset. That will come around and around and around again. So the type of data that you have dictates the statistics that are appropriate for you to use, and we will learn to use the statistics that are appropriate for the type of data. So we always have to identify the type of data. Now this one's really important, especially for us here, but also for distant students, and that is you always have to think about the characteristic that you're interested in addition to just the plain old numbers. Just the plain old numbers don't tell you what you need to know. You always have to say, well, what am I going to use those for? And that takes us back to the, quote, operational definition. When I say, and there was another example that I looked at the first homework and looked at the ones that you tended to miss most. One of them was a big, long story about the Albion plant and starting up a washer. And as you go through, maybe I should, you guys, plug yours. Oh, you already took it. Okay. One of the variables that they had an interest in was product quality. I want to have good quality product. So how could I define a good quality product?
Find a metric.
Number of defect.
I can quantify it any way that I choose to. I can define it. In that particular case, we define the quality of the product coming out of that particular process as what? Cleanliness. Now, I could define, and we're going to do a lot with cans because I have a lot of, they're easy to bring to class. I have a whole bunch in my office. In the future, we're going to bring some cans in. I'm going to talk about can quality. How would I know that this is a quality can? Well, it has all kinds of features and characteristics, okay? And we can say, well, I'm going to define quality of this can for my purposes right now is the absence of any dents, dings, or scratches. Okay? Or I could define it as the amount of load that it takes to crush that can. And I want that axial load strength to be very high. I don't want those cans to collapse unless it's under like really a lot of pressure. So I could define the quality as axial load strength. And there's all kinds of, we'll encounter a lot of those as we go. Okay, so measures of dispersion, centrality, dispersion, and also then shape. Shape is not related to a single value, but an aggregation or a collection of values. And the shape is important to us because it lays the foundation for what we will make the transition into in Unit 4, probability distributions, the distribution of the values in terms of their frequency of occurrence. And the shape tells us about that. And for those, let's talk continuous data for a moment. For continuous data, when that data is symmetric, uniformly symmetric around the middle point, and it can be rectangular, for example, or it could be pyramid shaped, or it could be bell curve shaped, so that if you cut it in half in the middle and fold the two pieces over, they would match each other. See, so my hands are symmetric around this plane in the middle. Now, it's not normally distributed. And so we talk about symmetry or lack of symmetry. When we have lack of symmetry, we call it skewed. It's skewed in one direction or the other. Okay? And we'll get more into that as we go. But generally speaking, and somewhere, it's probably in the slides as I recall. There's a picture that looks something like this. I just want to make sure that you understand what skew means, because over the years I have seen all kinds of weird things, and people that ought to know better apparently don't. So I know this stuff is stupid, but nobody else is going to do it for you, but I will. A distribution is skewed, quote, in the direction of its tail. Is there any question as to where the tail of that distribution is? Which direction is it pointing? It's pointing to the plus. Again, we think of our number scale, right? And this direction is plus, and this direction is minus. See, in the past I have actually read in statistics books that says if you consider a distribution that looks like that, imagine a big force coming in here and pushing on it so that it pushes it up like that. It is pushing it in the negative direction. That's negatively skewed. Wrong. Nope. It's not where it's at. It's skewed in the direction of its tail, of the tail. And if you just think tail whale, you're good to go. You'll never forget it now. There's certain things you just can't unsee when you see them, and this is one of them. This is one of them. Okay, so always remember that. Now, when you look at what's going on with these things, some important things are here, and let's play with the numbers. Let's consider a variable x. 3, 4, 6, 7, 8. 2, 3, 5. I probably could have picked better numbers, but that's okay. Now, I can calculate the average of these values, just add them all up and divide by 5. There's 10, 28 divided by 5 is what, 5.2 is the average. Now, if I want to talk about how much these values are spread out, historically, we have always used something called the standard deviation, and we start by taking the deviations of the scores away from their center, defined as the mean. Okay, so if I write 5.2 over here, maybe I ought to be writing 5.3, right? You didn't catch me. You guys are falling down on your job. Your job is to keep me from lying to you. 5 into 28 is 5.3, right? Or is it 14? No, okay. 5.3, 5.3, 5.3, 5.3, 5.3. Now, I should have done something to make that an integer. Let me do that. It'll just make it a whole lot easier. So now I'm going to look at the deviation of the scores around the center point, around the mean. So this guy right here is x minus x bar is 3 below the mean. This guy is 2. This guy is equal to the mean. This guy is 1 above the mean. And this guy is 4 above the mean. Does that make sense? Now, I can look at those values and get a feeling of how far the scores are away from the mean. If I say I have a score 25, that's a long ways away from the mean compared to these guys, right? So the amount of dispersion away from the mean tells me about, well, the distance from the mean tells me about dispersion. So why don't I simply find the average of those? What do I get? What's the average dispersion? Come on, you know this. Just have to look at it and tell me. 0. That is always, always, always the case. The mean is the point in a distribution where if you have a frequency representation, if you put a fulcrum, the distribution will balance. It's the balance point of the distribution. Those of you who have physics, it's the first central moment. Okay, it will balance. So even though it's a good idea, we can't go there. Well, one of the things that we can do to get rid of those, we have 2 things that we can do to get rid of those minus signs. We can square them, or we can take the absolute value. Let's do both. 9, 4, 0, 1, 16, and absolute value, 3, 2, 0, 1, 4. Now let's get the average. Okay, so this one is what? 4, 5, 10 divided by 5. So this guy, the average of these absolute deviations from the mean is equal to 2. Am I okay? Okay. And I'll never get angry if you correct me, especially when I'm wrong. Now, I might be disappointed if I'm right, but you'll find that you're right more often than I am. So, okay, so now let's do this one. 16, 26 plus 4 is 30. Did I do that right? 20, 30 divided by 5 is 6. Now, you'll notice that this average value right here is a squared term. Okay? So if I want to talk about it in the original metric, I've got to take the square root of that guy to put me back in the neighborhood on the same metric. You with me? Okay. I'm going to change on you here in just a moment, so don't get angry. So what's the square root of 6? I didn't bring a calculator. So we got R open, type SQRT parenthesis 6. It will look a lot like this. SQRT 6.
0.45.
2.44949. Okay, let's call it 2.45. Is that good enough? We'll have a lot of trouble. We'll fix it as we go, but we'll have a lot of trouble this semester dealing with round-off error and precision. What happened? Oh, that's why. Okay, so 2.45. Well, that's kind of pretty close to that.
The mean of 3, 4, 6, 7, 10 should be 3, not 6.
Which one?
The mean of the first column. The mean of 3, 4, 6, 7, 10. The first column.
That column?
Not the first one.
Way left.
The
First
mean of
column.
the value is 3, not 6.
10, 20, 10, 30.
I just
Divided by 5.
I just put on R. Mean of this value give me 3. Yeah.
The minimum would be 3, but the average is 5.
Okay, I put the function mean. Mean of those value give me 3.
Yeah,
Put on-
because the minimum value of those is 3. Going for the average, not
Yeah,
the,
if you type in min, M-I-N, it'll give you the minimum.
I type MEN.
That's
and
MEAN, yes.
M-E-A-N.
Yeah, you can put it on the R. Try it on the R.
You've made a mistake, but let's do this. Okay, so
Min?
what this is instructive. Let me do it up here so you can see.
Mean
Mean
3, 4, 6. Oh, you have to convert 6.
mean of these values. Oops.
3, 4, 6.
And what are the numbers?
3,
4,
4,
6,
6.
7, 10.
3, 4, 6, 7, 10, was it?
Yep.
We okay?
Yeah.
Now, I could have taken this, control copy it, and called it X for my values. X gets that. And
Of X.
let me put that around there. And it will display the results for us. Oop, when I hit Control Enter. So it just gives me those values, what happened. Oh,
Missing the close of the
One more.
parentheses.
yeah, I didn't have a closing parenthesis. Oh, this will happen. I have this trouble all the time. If I go in here and type a parenthesis, it knocks the one off the end. So you got to go clear to the end to put in your last parenthesis to match. Oh, it did it again anyway.
Okay.
What the?
So you're good. You just need to escape out of the console.
Okay, 3, 4, 6, 7, 10. Now, if I tell it I want the mean of X, it will do that. The minimum of X. Oh, R is case sensitive. Forgot to mention that earlier. So I have to type lowercase m for the minimum, and I can get the max.
Same one.
Oh, that's okay. I'll show you a little trick here. This is not something you want to do all the time. But if I highlight just that, it will only execute just that piece. Okay. All right. So we're okay. We're good with this. All right. And so now I've got over here, I've got something that's called the standard deviation with one small exception. Okay. I have 5 numbers, and I want their average to be 6. Okay, Robert, what's your favorite number in the whole world?
5.
5. Come on, be creative. Okay. Okay. Can I still get to an average of 6? How many possible numbers could Robert have picked? Infinitely many. What's your favorite number? That's okay. 1. If I'm going to have a mean of 6, I have to have what? What does the sum have to be?
30.
Has to be 30. Right? If I want a mean of 5 numbers to be 6, then the sum has to be 30. Which favorite number? Question. Can I still get to a total of 30? How many possible choices did he have to put in that spot? Infinitely many. Work with me here. Jesse, what's your favorite number? Oh, come on. Never mind, Jesse. I'm going to give you my favorite number. Minus 34682.793021. How many choices could I have used in that 4th slot? Can I still get to a total of 30? How many choices do I have?
Now 1.
There's no choices. There's only one number that's possible. Okay? Does that make sense? So, of these 5 values, n equal 5 values that we have, how many of them are, quote, free to take on any value and still meet the requirements? N minus 1 of them, 4. That, ladies and gentlemen, is degrees of freedom. Degrees of freedom. Degrees of freedom are almost always associated with the calculation of a measure of dispersion called the standard deviation or the variance. So instead of dividing this guy over here, the sum of this guy of 30 dividing it by 5, we would divide by 4 to get the standard deviation that we are going to work with. Okay, so if you take 6 and 30 divided by 4, we get what? 7.5? And then we'll take the square root of 7.5? Okay. Now, that standard deviation, before I take the square root, if I just take 30 divided by 4, that value is the variance. Statisticians always talk about variance, but it's hard for us to interpret it straightforwardly. So the first thing you do when you see a variance is you mentally take the square root, because that puts it back into the original metric. Okay? And that n minus 1 is in there because what we're trying to do is to make a statement about what we have in the sample and use it as our best statement as to what we believe the population dispersion is. And in order for that to happen, we would have to know the population average to calculate the deviations around it. And in order to know that guy, you have to have these guys add up to a certain value, and only n minus 1 of them are free to vary. That's kind of where it's at. But the important thing is, and in the text it's written, this is what I call the n minus 1 stuff. And I'm laying the foundation for doing more of that here in just a moment. So the standard deviation is a measure of dispersion, and the standard deviation that we're always going to use has the n-1 stuff in it. Now, when you have or use a calculator, there are two versions of this standard deviation. One is based on dividing by n, and the other one is based on dividing by n-1. Depending on the calculator and the manufacturer that you have, they will call the one where you divide by n-1.
Simple.
I've seen it both ways. In the old days, it was the difference between Hewlett-Packard and Texas Instruments. One would call one the population standard deviation, and the other one would call the sample. And they've had them switched. And so if you're going to use a calculator, just read the documentation so you know what they're talking about. But for us, the one with n-1 is the one that we call the sample standard deviation, and it is also the estimate. We don't talk about estimation formally until unit 7 or 6. Okay? But for now, we just learn to use the ones with n-1 in them because they give us the best statement about the population based on sample data. Okay, and in that unit, there's stuff on populations and samples. I'm not going to go into that. It's pretty straightforward. And so we knew. Okay, so now we have another measure over here that is directly an average. It is the average of what? The absolute deviations from the mean. The average of the absolute deviations from the average or the mean. So these values right here are called ADA values. Absolute deviations from the average. ADAs. Now, for reasons that we will cover in the future, it sometimes is better to talk about deviations from the median rather than deviations from the average. Okay? What I'm doing for you right now is I'm defining for you a binary that you're going to be asked to do that's due next week. It's called ADA and ADM. These are absolute deviations from the median. Okay? Now let's do that. Well, first of all, we got to calculate the median of these values. What's the median of those values?
6.
6, right? Shucks. I was too clever by half. I should have used an even number here. Okay, so I'm going to get exactly the same values over here, right? 3, 2, 0, 1, 4. And when I take the sum of these guys, I'm going to get, what did I get before? Well, I'm going to get, what, 10? And when I divide that by 5, I'm going to get 2. I'm going to get the same thing in both cases, but these are ADAs and these are ADMs, absolute deviations from the average and absolute deviations from the median. They are both measures of dispersion or spread in the data. Standard deviation and variance first, ADAs and ADMs second. Okay? Now, one of the binary that's going to ask you, it's going to give you some numbers, and it's going to ask you in Excel to do exactly what I've done right there. No reason for you to miss it. Binaries are easy and free, but I want you to understand the concept of dispersion. Okay? By the way, LOLCat has a function that will do the, 3, 4, 6, 7, 10. Actually, you made me write these down, 3, 4, 6, 7, 10. Okay, now watch this. ADA gets dispersion dot, now this is cool. When you start typing a command in R or LOLCat, it will automatically populate. As long as you spell things right, DSPERSION. Okay, now dispersion, and the reason it's not doing that, let me go back. And if you wait for a moment, it should auto-populate. If it doesn't, and you're impatient like I am, press tab. Oh, Okay, I planned this. I know you don't believe me. You think I'm full of crap, but I'm not. What has happened? Every time you start a new session, and I forget this all the time, you always have to tell the software to use the functions in the LOLCat library, and I haven't loaded it yet. Now, there's two things to do. Number one, if you click over here on Packages, and it's going to take this a long time because when they installed R on this thing, they went out to the CRAN library and they downloaded everything. So it takes it 30 minutes to, so I'm only going to do this once. And you can see that it's still thinking about it. But then it's going to list all of the functions that are there in the packages. And you can scroll down and you can just see there's a ton of them. I want to do some checking here. As a matter of fact, it's probably so many.
Search, capital.
I'm looking for.
Or cut.
I'm looking for car first.
Just put search. You see the bus.
Since I'm on the way, I can probably type it in and get it. Well, at any rate, I'll launch it. JK. Now, this guy might not have. Okay, so one thing you should do in your code is do this. The way you make a package active is you type in require. And then we have to install underscore GitHub quote burrm / lolcat. This something that you should have done already, and then I have to require it. That's what makes it active in our session. Every time you turn your computer off and then turn it back on and start an R session, you have to tell it to require LOLCat. It will already be stored in your library of functions, but you have to make it active. So I have to run, I put this at the heading of all of my things just in case, so I always have it there. I don't have to memorize those functions. Did it? Control. Okay, it's working. And it'll take a couple of minutes to do this. So we just added dev tools on the other side. Now it's activating it. Now it's going to get LOLCat, and then it's going to require. Okay, so it's there. Now, if I looked over here, I would have it. Now, there's something else that I want you to do. So this is not in any of the other instructions. I just discovered I wanted to do this today. So I want you to. Install packages, car, C-A-R, and then require car. And since I'm doing this now, I'll just go ahead and do that and get it done. It turns out that the car package is one that's used for, it's a companion to applied regression analysis. We're not going to do any regression analysis in here, but it has some really nice utility functions, which you'll see a little bit later tonight. Nick?
Oh, I just wanted to make sure, is the command require the same as checking the boxes?
Same as checking the boxes. Yeah, on yours, you're not going to have all these. So you can just go to that package, as you scroll down, check the box. And you can also use the command library, parenthesis, whatever. Either one of those will work. They do the same thing. Okay, so now that we've got that, now I'm going to go back up here, and now I'm going to take ADA, dispersion, DISP, and you'll notice it pops things up. So now look at that. There's dispersion, ADA. Well, that's cool enough. Just click on that. Now, what do I want to make the ADAs of? The stuff that's in the variable X. And I want to print that out, so I'm going to wrap that inside of parentheses. And there they are, 32014. So we have a function in there to do that. Now, if you had to write your own function to do that, it would be easy enough to do, right? You want to see it? Okay. I have something that I want to be called ADA.Ray. That gets the following. It's going to be the absolute value of X minus the average of the X's, mean X. See, I got functions inside of functions inside of functions inside of functions. So I'm going to take the absolute value of X, which is a vector, minus the mean of all of those X values. And that should work. And now let me wrap that in parentheses so it will display. And we hope that Ray has done it correctly. Whoa, woohoo. Look at that. Now, if we wanted the other one, now that I know what I'm going to do, ADM.Ray gets absolute value of X minus what? The median of the X's. Does that make sense? I always type, I'm looking at the keyboard while I type, and then I'll check that. So, okay, so that should work and give us actually the same values, right? And it does. So this allows me to, again, just give some code in R so you can begin to, so that you can say, I can do that. If he can do it, I can do it. Okay, but we're putting a function inside of a function, and we're doing some operations inside. So that's just kind of handy little stuff. Now, if you want the standard deviation of the values in X, you can type that. If you want the variance, type VAR of the values in X, and you'll get both of those values. Okay, if I don't do it right now, you won't get a break. Let's take a break. Come back. I've got a bunch of other things I need to make sure that I cover tonight. But I wanted to make sure that you have, since you did quite well collectively as a class and actually individually as well on the prep quiz for Unit 2, I want to hit the high points and make sure that you feel pretty comfortable with using R. So I think I've got out here somewhere a, did I do this last week? Maybe it wasn't this class. Did I do this last week? Okay. So let's take a short break.
Sure.
Can you display the R?
What's
Can you
that?
display the R? I want to see the R. Display the stuff you have been doing.
I can't.
Can you just display the R, but typing the...
Oh, do you want the R screen?
Yes, please. Okay, you can put small if you want.
That's okay. Yes.
Can I get your John Hancock on this?
Oh, yes.
And what's your expectations in terms of doing this? I'm happy to do all the work. Additional grading efforts, but
Yeah, what I'll do is I'll set you up so that you can do all of it.
okay, great.
And I think that's it. Let me. Okay, and
Your
you,
name is Ben.
Ben?
Yeah, it's actually Bennett, B-E-N-N-E-T-T. Last name is Guderian.
What?
G-U-D-E-R-I-A-N.
And what's your, are you BEGA?
E-G-U. I don't have it right.
Yeah, and then there's a number.
BEG 6935.
Okay, with that, I can add you to the course website, and you'll be able to do that. Okay, you have that. Yeah, and you'll be. I'll actually enroll you in this class, but when you actually register, then they will push you over, but it'll take 24 hours. So I'll do this tonight, so you'll have access to the course, and I'll talk to people in
And
the
the function
morning
dispersion,
about.
you know that?
About getting you access to the honor code.
Dispersion
So I'll
of
do
ADA.
that first thing in the
So you
morning.
need to make sure that you load LOL kit.
Yes, yeah. If you want to hang after class for a couple of minutes, I'll give you a
Yeah,
guided tour.
just a second.
Okay, so what Diane, I need her, okay. You can do this, right?
Yep.
You can do this, right? Yes. How about you? You're aerospace, right?
I'm an English teacher.
What do you do? English teacher. What are you doing over here?
Yeah, good work.
Welcome. You're welcome.
Yeah. So I actually teach international English,
Oh,
technical writing. So I have a lot of engineers.
oh, okay.
And so I figured if I'm going to teach them how to write, I should probably understand what they do.
Well, I'm glad to have you. This will be an enlightening class for you, I hope.
Yeah, it already is.
Already is. Good. Okay, did we get you straight? What was wrong with your R installation? You just had to reinstall
Here's
it?
what happened. Even I reinstalled it, it did not work. What happened in my operating system, I was not able to get library installed. So what I did, I installed another machine, I just copied.
Oh, yeah. Your brain on statistics. What's this? This is your brain on statistics after I get done with you. See, it's a lot funnier when I do it at the right time.
Yeah.
But Jesse said it's so cool, you just have to do that. So there you have it. Actually, this is your brain, and by the time I get done with you, it's probably just the reverse of that. But okay, what I want to do next is to give you some information on how to bring stuff into R. We've done a fair amount of little diddly-piddly low-level stuff. So we'll have that. Next, I want to talk about bringing data into R. Now, we'll do that by looking at, starting early on, there is a data file called, what, is it motors or noise? Voltage. I think it's just motors or modules. Oh, modules.dat. Okay, on the website, and you should have downloaded that onto your own computer, a big zip file that's got hundreds of data files in it, and I think it's almost every data file we're going to use this semester. As I go along, I might add to it and upload and tell you to re-download those extra files, or maybe just put them in a smaller zip file so you'll have everything associated with the class. There's a bunch of ways to do this. There's the easy way, and then there's a hard way. Let's take the easy way first. And I didn't finish this. In the upper right-hand corner is the Environment and History panel. I'll call it the environment panel, because we'll almost never going to use history. Now, if you click on history, by the way, and you can resize these, is the list of all the commands that I've typed tonight so far. That's typically nothing that you need, so we're going to cover that up. But in the environment, it lists all of the variables that were created. So I created a variable ADA, ADA Ray, ADM Ray, D factor N, N2 and X. These are all variables and things that I created tonight. Down here on the bottom right-hand side, you have a listing for a directory listing for your files. When you create a plot, they will appear over here. So this is all called the plot window over here. You've already seen packages. Help is a wonderful little resource. If you have a question about any function and how it works, just go to the console over here and type in a question mark, let's say like box plot. We're going to talk about box plots. I was leading up to that, but I'm going to jump past that for now. If you want to find out about a box plot, just type box plot and then press enter. And it should it will give you information about the box plot. It will give you the nature of the function. It will give you all of the arguments that are in there. And when it has something like range 1.5, width null, these are all things that it pre-establishes as the default setting. Null, 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 nothing, 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 nothing. And so all you have to do is enter X, and it will tell you what X is. X is a variable, or in some cases a data frame, and it gives you information on all about the things that are available. Notch is an interesting function. I'll show you that. You don't have to use all of those functions. It gives you a couple of examples. The examples, in my opinion, are usually fairly high level and complicated. I find I don't get as much use out of the examples as I hope that I would when I'm scrolling to find them. But it gives you some ideas about what can be done. So now up in this upper left-hand window in the environment, there's an option right here that says import data set. So if you click that, you have an option to bring it in from the web at some URL. We won't do that for this class. The only thing you'll have to do is to do local. And then you just have to browse to wherever you have saved your data files on your computer. Question?
My drop-down menu is slightly different.
Yeah.
Mine is like CVS, Excel,
Yeah.
SPSS.
So in the
Oh, you have a whole bunch of those options there? Oh, okay. You'll never have to worry about SPSS. CSV stands for comma separated values, and numeric values are separated by a comma, and text values or character values are inside of quotes. And so it knows that, and it expects those, so it won't read the commas as text. It will read them as separators. Okay. There's
Our file's a .dat.
all of our files are .dat. All those files are ASCII text files, and they're in columns, and they're delimited with a tab. They're tab delimited text files. Okay.
Like it would not qualify as the options that drop-down menu.
Say what?
so
What are the options in your drop-down?
Can you spin it around?
That's not an option.
So on this new version of R, I don't know why they did, or sorry, R Studio. I don't know why they switched to a new library for importing the files. And so once you can click on any of them.
Should be able to do CSV.
Once you find the file, there'll be a
Yeah.
pop-up, and you can actually change what
Watch this for just a moment. So for right now, do this.
it looks slightly different.
Select CSV. And I'm going to navigate to my flash drive here.
Package to be installed.
Oh,
This is what I was saying.
you have to update the package.
Yeah, so just say yes to the
To be
package.
installed a new one?
Yeah,
He will do it for you. Just so,
you can just click
yeah,
yes.
yes, he's understanding it.
Okay, and we're going to go get the first file, which is named modules.dat.
Have to read.
And when I tell it to open, I'll wait. You should get a window that looks something like this.
Updating the package. Please updating the package what I said.
Oh, you're installing a package? What is it?
CSV.
The CSV.
They did something other than foreign.
It looks different now. So
It's not the same as foreign. Oh crap.
Now I ask for the file.
Yes.
and stuff. See, now I ask for
Thank
the
you.
file, units.
Yeah, just browse for the file that you want.
Or binary. Or which
No, it'll be under data files. Wherever you saved that data files zip file and unzipped it. Wherever you put that.
What's the zip file under on G12?
It's under data.
So not under IU2?
No, it'll be up right there. There. Oops, sorry. Yeah, just click that guy and it's a zip file. Just download it and then put it where you want it. Open it.
So when I first opened it up, so this is looking for a file, and there's no modules. But then if I go back into zip my main files,
Picture and so forth.
I go into files, it shows up, but not when I try to import it.
That's cool.
No.
I can't see.
Somehow, I don't know what
Not
I
under
did.
IU2, I
I
don't
don't know
know.
what you did to get that.
Yeah.
Well, you navigated to that somehow.
Yeah, so this is the unzipped, and then it
And just
prompted
click, and maybe it's already in there somehow. Just click on that box. No. Oh, yeah, no, okay, yeah, click that. Okay, no, okay, so you've got it. It's in. Oh crap, that means I'm going to have to install a new version of RStudio.
Yeah, this is like pumpkin spice version or something.
It's what?
Let me go to the top. It's called Sincere Pumpkin Patch
Okay.
from 1031.
Okay, do you have it in? File modules in?
Downloaded it. I'm gonna play with it. I'm gonna see if I can figure it out.
Did you get the data file in? You got it in?
it's not
Morgan,
giving
did you
me
get the data file in? Working on it, okay. How do you say that?
Working on it.
How do you say your name?
Khushbu?
Kushbu, okay. Working.
It's loading. Why is loading?
Working. Okay. I don't know if you'll ever see anything like this or not.
So I open the file.
different.
A lot more expansive.
Thing encoding, but
Things were a lot simpler when we had Model Ts. You could work on them, you could fix them with baling wire and chewing gum. You don't have any damn computer on the thing to have to fool around with.
All the data has been loaded here.
How do I do that?
So go browse.
What's that?
Yeah.
Oh,
I got
And then
the
find
I
the
got the data
file.
from the website. Should be this, yes. This data? That's fine.
Okay, there you go. Okay, now it looks like they're there. So just scroll down. Those are all the data files. Scroll down to
Which one? Which one?
modules.
Oh,
Modules right there.
okay.
Okay, and then you should be able to open it. I don't know how you open it.
Yeah, I have to go back to this in my head.
So when I clicked on the where I unzipped it, that's what
Encrypted file
I
instead of encrypted file.
So I'm not sure what that means. I just hit yes, and it popped up rather than import.
I've gone it
There
to
is
work.
something weird.
That probably is what did that. I don't know.
So is
So
that the
now,
same thing, just a little
yeah,
different, or?
yeah, no, this is just a new
Because then it
version.
goes through all the, and then all the data files that were.
Oh, that's
You need to unzip it.
And so they're also now in the future, you might just, all you might have to do is to go to Files, scroll down and click on it, and it might just open it. I don't know.
Interesting.
We'll find out. We got 2 or 3 to do here.
Okay.
Okay, is everybody at least halfway with me? Did you get,
Yeah, so this is what it looks like. It does seem to be open, and we have different types of files in here, so I could probably just like click
Yep.
on whichever one we want.
yep, just scroll down in there until you find modules.dat.
Thank you. I just
Maybe it's at the top.
Yep, it's fine.
They should be alphabetical order, I would assume.
I would assume two.
Right.
It's
Once they're in, it's.
wait. Oh,
There you
there's
go.
time dependent. Okay, so it's like, is there like a specific
You
year?
know,
it's
same
from?
thing.
Oh, gosh, I don't know. Just tell this guy to look at,
I just
tell
actually
the Mac to look at these in terms of
data from my
not
students.
time order, but by
104
name.
different GPAs and just
Going
yeah,
into my files.
yeah, and see what the
What is the complete name?
It's compressed. There's a
Modules.
folder inside of a compressed folder, so you have to extract two of them.
it'll automatically display. And those are all
I'll play around
Well-
with it some more. It's like going into my files. It's not like actually searching within.
Yeah, all I've done
You
up to
get-
this point is just like I think he's got the 2 videos.
Is it like an
this is one
Excel
thing.
file? Or?
No, it's a DAT file.
They're helping.
Yeah, it's very neutral. All of these data files are ASCII text. They're very neutral, so they should be able to go
It doesn't
into
have a problem
anything.
with it. Doctor, it doesn't have a problem with it. If you open up the .dat file,
For some reason, it's
It just,
necessary to have.
yeah.
Not just
Now, with one column, that's true, but when we get
yeah,
10
just like
columns,
C. Exactly.
we might have troubles in the future.
The one you told us to open worked up just fine.
Try opening Rivet. Yes. Because that's got 2 columns of data in it.
It gave you
I think if you change that to,
It was the binary that had the dispersion one.
Yep.
right.
Yeah, under IU2.
See if it actually separates.
The importing the data the same as importing.
Paint and Rivet looks like there's 2 variables.
I just
in
clicked
there.
on the unzip file and then.
Oh, yeah, I guess, but they're not separated. I would expect them to be 2 different columns. Looks like they're
Yeah,
one column.
yeah, they should be.
if you change the delimiter to tab, I think it'll do it in separate.
Yeah, yeah. So,
File type.
Like if I
yeah,
use-
well, the file type will be the same, but there'll be an option somewhere to have it as delimited with a
I
tab.
didn't import anything. Like I.
These are all tab delimited files. There you go.
Okay.
Now do the same thing, and then it should come right in. Well, crap, I was set up to just,
That changed maybe. So it didn't.
no, everybody else had the original version. Okay, these files, just so you'll know, are very neutral. They're ASCII text files. They're delimited with a tab. Robert just showed me that on your input screen, down along the bottom, there will be something that says delimiter, and you want to select tab, and then these will come right in. And I think you started with the CSV, and then you can ask, because with comma-separated variables, file formats, over the years, they have changed so that you can delimit them with other things, and then the delimiter parameters set that up. Did you find?
Okay, so it's giving me an error message that says it has a magic number and use of saved versions prior to 2 is deprecated.
I don't have any idea.
I'll play around with it some more.
Okay, so everyone is good except Emily. And it's Emily, right? Yeah. Good. Okay, well, you're bad. We'll fix you in a minute. Okay, the way it used to be was very easy. When you brought the file up, it would ask you for a name. It will put the name here of the name of the data file, and then you always, in almost all of these files, there is a header which tells it that it's the name of the variable, and so you say heading yes, and there'll be something similar on what you're doing. If you say no, you'll notice that it says, okay, well, you don't have a header, so I'm going to treat that first one as data, and so I'm going to give you an automatic variable name called V1. Well, that's when you know you're not doing the right thing. So we do have a header. Now, here you can do anything you want. I tend to, as you'll see in a moment, I tend to put the name of the data file has a name, and we're going to bring it in, and when it imports it, it's going to put it in something called a data frame. A data frame. It's like a data file, but the R word technically is data frame. So I'm going to put this in a data frame called lowercase m. lowercase m. You can use anything you want. If you want to just use the data file, well, let me use modules because that will match the stuff that's in your book. So I'll just leave it that way. Capital MODULES, modules. And voltage is the name. Now, this one is a little bit tricky because the font, the default font that is used here, it may not look like it to you, but that is a capital V on voltage, not a small case v. It's an uppercase V. So when I tell it to import, it will bring that file in, and it will show it as a file. And over here in the data area, it will tell you modules. So if we have other ones, then you can kind of go over here and scroll and just click to the data file. But I typically don't need those open other than to just look at the name of the variable. It's capital V voltage. Now, what I do personally is I go down here and capture that command, do a control copy, and then I go up to where I was building my code and do control V and paste that so that now in the future I can simply type that thing and it will go get the data file. Now, I have a little bit of trouble with that because I have it set up to recognize where these files are on my own desktop computer, but then when I copy these to the flash drive, in the flash drive, every time I plug it into a different device, it registers as a different drive letter. So I have to fiddle around with that. But for this class, at least for me, it says, so it does say it's going to read a comma-separated variable file with this is the name and the separator here. When you only have one column, you don't have to worry about the separator. When you have two or more columns, then it gets a little bit dicey. There are separator codes. If you ever have to enter a separator code, for us it would be \T. When you select the tab option, it puts that in there. It says it's a tab. And then you can also put in, is it header? Yeah, header. Now notice when I started typing, see it filled in, so I can just press enter. Oop, I guess I can't. And the header, so it says HEADER, so I can say header, and I can say true. You'll learn more about when to use true and when not to. Now, a lot of these functions require an argument to be either true or false, and it's capital letters. Now, it is true that you can use a capital T or a capital F, but you don't want to do that because there's weird things that can happen. So when I do this and I hit that, it will reread that file in for me a second time. So I've got modules in there. First thing you do when you bring a data file in, is you want to do str and then the name of the file. And remember, R is case sensitive. So we're going to look at the structure, control enter. The structure of that thing says, it doesn't like how I spell structure. It's STR instead of SRT. STR. And it says, what you have here is a data frame. You have a data frame, and in it is a variable named voltage. Notice there's a $1 on the front of that, voltage. That's very important. And it's numeric. If it's a factor, it'll say factor there, or integer, or character, or logical. It'll tell you the nature of that variable. Then it has the value. So you just do that just to see what you've got. You always want to do that. Now, if I want to display the contents of that guy, if I just type in the word modules and run that, it will print out the entirety of that data frame. And in that data frame is a variable called voltage. Now I can access that individual variable very simply by typing in modules and then a $sign voltage. And as soon as I type that, it's looking inside of that data frame, and when it sees voltage, I can just hit enter and it will auto-populate. And when I press enter, control enter, it will display that guy. And this is one of the things that R does, is it strings things out as far as it will go. And it says, this is the first one, that's the 15th one, that's the 29th one, that's the 30th one. So that tells me there are 30 values in there. Okay. Now, if I want to calculate the mean of that guy, I can tell it to calculate the mean on the voltage variable, but I can't just type voltage. I have to tell it the data frame because there's lots of data frames over here. So I type in modules, $voltage, and it will calculate the mean for me.
What does mean 15 and like 29?
What's that?
On the left side, 15, what does mean 15? 15 numbers?
It's the 15th.
That's the 15th number in the vector, in the string. So that 15th number is 122. So if I go up here and look at the 15th number, it's 122. So these numbers, these are the values. These are so-called index positions. Index positions. So if I want the 23rd value of that variable, I have to tell you the data frame, modules, voltage. Got everything spelled right. And then in square brackets, 23. And it will go get the 23rd value of the variable modules, or of voltage in the data frame module. So you have to have this kind of continued addressing. So once you get used to this, you'll begin to realize that that is why I will typically name my data frame. A lot of people just use the data frame, they just call it D. So you just have to type D, so you don't have to type a lot of characters every time. Do it any way that you want to keep, that you can keep up with. So when I run that command, control enter, then it goes to find the 23rd. Well, there's 15, there's 16, 17, 18, 19, 20, 21, 22. There's the 23rd value right there, 123. Okay. Now with that, you can do all kinds of stuff. You can do the mean, and this is the kind of code that's in there. You can make a frequency table, and the code is in there. You can do a histogram, and you can do all sorts of other things that we've got the code in there for you to do. Let's make a box and whisker plot. A box and whisker plot is a really cool device because what it does is it is an ordinal-based measure that has in the middle the median. And then it has a box around the median that's based on the first and the third quartile. And then it goes out to an end point that is called an inner fence. So it's kind of like the fence before you, if you go beyond the fence, then you're out of the yard. That is, you're in outlier territory. And the length from the edge of the box to the inner fence is 1.5 times the size of the box. And the end of that whisker point right here is not technically the inner fence. That point right there is the point of the last actual data value that's inside the inner fence. Anything beyond that fence value is an outlier. And outliers are listed as, depending on the software, they can be listed as mild, that is, there's a distance from the middle to the fence, and then there's another zone from the inner fence to something called the outer fence. And anything beyond the outer fence is way out there, and they're called wild outliers. Anything between the fences is an outlier. Anything on the inside is, quote, typical. And this typicality is based on the fundamental calculations associated with a normal distribution. And we'll learn how to interpret that. Obviously, from the very highest value to the very lowest value is the range of the data, 25% to the box, 25 to the median, 25 and the other 25. So it's a very, very nice way to look at it. And we can actually compute one of these things by telling it that we want a box plot. Box plot of, what do we want the box plot of? Well, the variable that is in the data frame modules, $voltage, And then I'm going to put a notch on it. It's not, a notch is not listed in here. This is just an extra thing, just kind of like an extra option. So I press enter and put true. Yes, I want a notch on it. And when I do that, I get the same kind of box plot that is displayed in the manual for this data. I think it's actually another data value variable that we used to create a box plot. But a notch is, this will make absolutely no sense to you right now, but in the future will be very important. If we took another sample of data from the same set, the same population, another sample, and calculate the median would probably be different. Every time we get a new sample, the median will be slightly different. And the amount of difference in those medians from sampling to sampling to sampling to sampling, we can talk about how much variability there is among them, and 95% of the time, they should be inside of the boundaries identified by the notch. So that ends up being a pretty handy thing. We'll talk about that in the future. So the true median of the population could be anywhere between a value here and a value there. For our sample, it happens to be there. So that's a little handy. Now, I was going to show you something else. T or F. It gets true. Okay, now I'm going to execute that command, and then I'm going to display the contents of T or F. And what should it show me? It should say that it's true. Okay. So if I go back up here and change that to false, and I'm going to make it easy on myself, I'm going to do this. I'm going to put parentheses around that so I don't have to screw with that. So now when I display that, it's going to say it's false because I assigned false to it. Okay? Now, here's the thing you got to be careful about. T gets false. Okay? Now, if I use a T to tell it that I want to have a notched box plot. So now I'm going to go back up to here, and now I'm going to tell it I want a notch, true. I want a notch, true. But when I execute that command, I don't get a notch. Why? I told it I wanted true. Well, the letter T is a variable that has a value false assigned to it. So you can get yourself into trouble because of stuff like that. When you're running a lot of these other packages, somewhere inadvertently they might set a value to a T or an F that you don't want. So I recommend that you always type out in full anytime you have the opportunity or the necessity to type in true or false, that you indeed type in true or false. Question?
True, 1 or 0, or does it have to be true or false?
It's a logical variable. I think if you assign it a 1 and tell it it's logical, it will convert it to a true or false. I haven't played with that. I just check it out and see. Emily, did you ever get resolution on getting a data file in? Yeah, just the output. Okay. We only have half an hour, and I want to. We covered variance standard deviations. There are a number of other measures of dispersion, the interquartile range. If you take that interquartile range and divide it by a magic number, it gives you the equivalent of a standard deviation. We'll talk more about that in the future. But for right now, this is important. Relationships and association. Okay, I'll have time to do this. This is important. This is important. Okay, we were here some time ago looking at measures of dispersion around the middle. Now, it turns out that if I take x minus x bar, earlier we squared it. When we played with that, we ended up getting the variance. Correct? Now, in the past, people have taken to the habit of raising these things to the third power and to the fourth power, plain old deviations. Now, it turns out if you have a distribution that looks like that, or one that looks like this, if you do this, notice the mean is going to be in here somewhere, and in this one the mean is going to be somewhere like that, the balance point. Now, it turns out that when I start taking deviations of these individual x scores in this distribution, when I look at x minus x bar, and I'm talking about this x, then that's going to be a positive number, right? And it's going to be big. And when I raise it to the third power, it gets really big. Okay? When I take a value down here and put him in, he's going to end up with a negative value, but it's going to be a small value. And when I raise it to the third power, it will be a lot bigger, but it's still going to be small compared to everybody else. So when I take these guys and add them all up, you can see for a distribution that has this shape, that sum is going to be a positive value. On the other hand, if I'm down here, when I put this guy in to that formula, I'm going to get a big negative value. And when I raise it to the third power, it's going to be whoosh, way down there. And when I raise it to the third power, it's going to go minus, squared plus, third power minus again. Okay, so it's going to keep the minus sign when it goes that way and up. So when I take the summation of all of those guys, I'm going to end up with a net negative number. Well, this value right here, if I then divide by n, I get what's called the third central moment. And it is an initial trivial measure of skewness. Okay? And if you have a symmetric distribution, that's symmetric, that's symmetric. It doesn't have to be bell-shaped, but we talked about symmetry. Anytime you have a symmetric distribution, this guy's going to be 0. If it's different, so if you have a distribution that's skewed, this is going to have a positive skew value. This one's going to have a negative skewness value. So this now is perfectly in line with the whale analogy. Okay? Now, when I raise things to the fourth power, and sum those guys up and divide by n, one of the things that's going to happen is when I raise any value to the fourth power, I'm going to end up with a positive value. Okay? So in the past, some time ago, people used to use this for a measure of kurtosis. Kurtosis has to do with the relative flatness or the peakedness of a distribution as opposed to its symmetry. Where in the olden days when they did this, if you had a normal distribution and it met all the requirements for normal distribution, this value right here was equal to 3. That's bounded by 0 on the bottom side and plus infinity on the top side, but a normal distribution had a value of 3. And so some statisticians got together and said, why don't we make this easy? If we have a normal distribution, skewness will be 0. Let's go ahead and subtract 3 from this guy. And when we do, then if you have a normal distribution, the kurtosis will be 0, and that's the reference. So the normal distribution is the standard reference distribution. If a distribution is flatter in the middle, like this, that's going to be negative kurtosis. If it's taller in the middle, that's going to be positive kurtosis, where the normal distribution is the norm or the standard. Okay? Now, that's the simple version. The simple version. The more complicated, and there's two more complicated versions. I'm not going to bother you with the whole thing, but when we talked about the variance over here, we took the summation of x minus x bar quantity squared, and we found the average by dividing by n, right? But we did something else. We came in and divided by n minus 1 in order so that this guy would be a good estimate of population sigma squared. If we want this guy to be, and we call this, we're going to, in just a moment, if we want this to be a good estimate of the population skewness, Greek letters for population, gamma 3, population skewness. If we want this guy over here to be a good estimate of gamma 3, then we got to do some n minus 1 stuff downstairs. Does that make sense? And if I'm going to use this guy over here to be a good estimate of the population kurtosis, gamma 4, then I'm going to have to put some n minus 1 stuff down there. And that n minus 1 stuff gets pretty complicated. Okay? But when we're all done, we have a measure for skewness that we call G3 for the sample and gamma 3 in the population. This guy over here with the n minus 1 stuff in there, we call it G4 to estimate gamma 4. So what we're going to do is we're going to use these G3 or G4 and G3 values in our sample, and they've got the n minus 1 stuff built into them so that when the time comes, we can talk about estimating properly the population skewness and the population kurtosis. Now, in order for you to see and understand all of this, you have a binary that's called dispersion, skewness and kurtosis, and dispersion in moments or something like that. And it asks you to do some stuff in Excel to basically build exactly what I've drawn for you on this slide and the previous slide. And along the way, you're going to manually build ADA and ADM values by subtracting, and I showed you how to do it in R. I know you won't remember that. That's why you can go back and watch the video. Okay, but it's easy enough done, and that binary leads you through it. See, you could do that binary without me saying anything about this. You wouldn't have to know it. It just says do this, 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 do this. When you get all done, what's the answer? Do this, this, and this. And then when I can come back, I'll say, well, what you really did was this. But I wanted you to see the structure so it would be easy for you to do the binary in Excel. And then when you look at it, say, how could I do that in R? Well, it's easy. In R, all you'd have to do is take, I need to have x minus the mean, right? And then I'm going to have to raise it to some power, the second power, or the third power, or the fourth power. And then I have to sum up all of those, and I will get the value. So you will learn, you will begin to feel more comfortable with R and doing this. This is low-level programming, but you'll become expert at it before long. Then, of course, you'd have to come and put all the n-1 stuff in there. Now, the n-1 stuff is kind of hairy, but you don't need to be intimidated by it, because the fact of the matter is the software does it for us. And there's our dispersion spread. Here's our percentile or quantiles. It gives us percentiles. And there's variance, standard deviation examples. And there's the deviations from the mean and deviations from the median. Pseudo-standard deviation, there's the magic number, 1.34897. I'll explain that later. And so now we get to skewness and kurtosis. Now, this guy right here that I just did for you, the summation of x minus x bar raised to some power r divided by n, that gives you what's called a centralized moment. The second moment for variance, the third moment for skewness, the fourth moment for kurtosis. And then we come back and take that moment right there, that third moment, oops, the third moment, yeah. Well, what I ought to do is, that's why I have this. Well, maybe I don't. That third moment has dispersion already built into it. Does that make sense? If I raise something to the third power, then any influence that the second power thing had is in there. And we don't want dispersion to contaminate our issue of shape. And so we divide that out by taking the second moment, one half of the second moment takes it to the first moment, and then you raise it to the third power. So we're going to take this guy and normalize it by dividing out the dispersion part, and then this is the n-1 stuff in parentheses. It's built in automatically into the LOLCAT software. If you use any other software, like MATLAB or anything else, Minitab or other software, they all pick one way to do the skewness and kurtosis. They're not all the same. So you need to be careful if you use other software to do any of this stuff. The software that is written for this class is how it's taught, and the instructions are in there, and you'll always be doing the stuff that I expect you to do. Just be careful if you're using other software. Okay, so here the n-1 stuff is in there. Now, when we go to kurtosis, then notice here's right there in the middle is the fourth moment, and we have to divide that by the second moment squared to get rid of the dispersion part. Okay, then we have to subtract 3, and there's n-1 stuff on the 3 side and different n-1 stuff on the other side. So all of this complicated stuff, I don't even have those formulas memorized. I've been doing this for years, so don't even worry about it. But that's why I say it's got, the magic is the n-1 stuff is in there. And that's what gives us the good values in our sample that we can use to talk about the population when we get to that point. Okay? So that's the dispersion stuff. And you've got a binary to do this stuff manually or womanly so that you can actually see it and know what's going on.
So when they have the same value, let's say G1 and G3 has the same value, what does it mean?
If they have the same value?
Yes, G1 or G3, because they have different power, but they have the same value. Is it possible?
Sure. I can imagine it is, yeah. I mean, you can have a skewness, a G3 and a G4 that are the same value.
Yeah.
You just have to interpret it. That's kind of an interesting question. And as a matter of fact, I'll even call it a good question. Let's say that I get a G3 value of minus 2.6 and a G4 value of minus 2.6. What does the picture look like?
Short.
What does the frequency picture look like? Well, first of all, you know it's going to be negatively skewed, right? So I'm going to have something that looks like that. And this guy is going to be shorter in the middle than you would expect if it were a normal distribution. So in order to make this kind of conceptual, let me say that that would be a normal distribution. Then this distribution is shorter in the middle than the normal distribution would be. Now, what if this were a positive value? Let me change this to a different color. I like purple. I'm a purple guy, you can tell. Okay, so what about if that were a positive 2.6, then what? So it would be positively skewed, but it would still be shallower in the middle, so it's positively skewed in it, and it's negative kurtosis in the middle. Okay, now this is a warning. It is virtually impossible to see with your eye kurtosis. You can see skewness. It's pretty easy. But to see kurtosis, it's hard to see. Even if I superimpose a normal curve on top of it, it's still pretty hard to see. I've been doing this for 20, 30, 40 years of my life, statistics, and I am still amazed at my own gross inability to see kurtosis. That's why you never look at a picture without a number, and you never compute numbers without looking at corresponding pictures, okay? That's a mantra. We'll just go over it and over it and over it. And if you fail to do that, I promise you along the way, you'll make mistakes that you ought not to make, that you would know better if you had the picture, it's like, oh, I would never have done that. Okay? So the last thing, I've got 10 minutes. I might keep you 5 minutes over if you'll let me. So that's the skewness and kurtosis. These guys have, just think of it this way. Negative kurtosis is kind of flat. The technical name is platykurtic. I used to, when I would use those terms, I call it flatokurtic. So it's kind of like a plateau. It's flat. Flatokurtic is minus. And picate is positive. Positive kurtosis, pictokursis, and flatokurtic. But you don't have to worry about, I'm not going to ask you to, the Professor Luftig used to insist that people learn those names for it, and it's all crap. It's either positive or negative, according to me. But then I'm not a millionaire, so who's the dummy? You can actually get skewness and kurtosis values automatically this way, but we'll almost never do that. The commands are there. We're going to use some other kinds of functions to get skewness and kurtosis because it's going to do testing for us along the way. We'll learn about that starting in Unit 4. But you can get skewness and kurtosis values just by typing those in. And now with what we've done tonight, you can actually go back through, read the data files, get used to reading data files in and issuing the commands so that you can reproduce what's in the text manual and you'll be good to go. Okay, I mentioned earlier that I do want you to install the package CAR, C-A-R. So make sure that you have that done. And the reason for it you're going to see in just a moment. The CAR package does some really cool things, especially as it comes to dealing with relationships. When we talk about relationships, we're talking about correlation or association. And in this case, we have to have two variables. We want to know the relationship, and we're going to do this in the future, between height and weight. Relationships are either positive or negative, or there's no relationship at all. A positive relationship means that scores on one variable, oh, come on. I don't have a whole bunch of them. I was planning on drawing them, so I better do that. Okay, I have two variables. Usually they're called X and Y. And if we plot them on a rectangular coordinate system like you learned in algebra all those many years ago in secondary school, this shows, and basically you can do this. You can mentally put a straight line through there, and the slope of that line gives you the nature of the relationship. Positive slope, positive relationship. That says values that are out here that have a large, so down on this axis we have small values down here and large values up here, right? So large values on the X variable correspond with large values on the Y variable, and down here small values on X correspond to small values on Y. So we talk about that as being, they change in a positive and a similar way. If, on the other hand, the swarm of these points, which, by the way, has a name called a scatter plot. Scatter plot, very good. See, nobody laughed at her. And I didn't mock her. I mocked her before, but not now. Okay? So this show is a negative relationship. That says for X and Y, for large values of X, you have relatively small values of Y, but for small values of Y, you have rather large values of X. So it's an inverse relationship. If there's no relationship, then the points will basically form a roughly circular pattern, and no straight line is a good one. And so in those cases, what we do is we draw a flat horizontal line. So zero slope is no relationship, but there is scatter. And this is scatter in two directions. There's scatter in the Y direction, the X direction, and there's scatter in the Y direction. Okay? And there's ways to talk about the measures of relationships for, and we have, obviously we have two variables, X and Y. Oh, but by the way, only one sample. Let's assume that we are a sample of the people that attend or have something to do with the university. We each have a height and a weight. We have 2 variables. We have 1 sample of n people. Okay? So sometimes people get confused, and so I make it explicit. So now, when these 2 variables are continuous and continuous, both of them are continuous, there is a special kind of correlation called Pearson R. We use the letter R, and it stands for the product moment correlation, the Pearson correlation coefficient. If these 2 variables are ordinal and ordinal, we have something called Spearman correlation R, and we usually put a little S down there so you know that it belongs to Spearman. Okay? And if we have 2 value variables that are nominal and nominal, we have what is referred to as a contingency coefficient. And there's basically there's one contingency coefficient, Kramer's V. Technically, in the past, there were 3 measures. There was Pearson's phi, Kramer's V, and Pearson's C. This guy is for a 2x2 table. This guy is for a square table. Let's call it M by M. And this guy, so this is 2x2, this is square, and this one is rectangular. R by C, rows by columns. Pearson started all of this after he did his work with continuous. Spearman came along and said, well, if you take his data and treat it as ordinal, you get this. And then Pearson says, oh yeah, well, if I take your crap and reduce it down to nominal, then I get this. Not only that, if it's a square table, this is how you do it. And Kramer came along and said, well, my coefficient is for rectangular, and Pearson had to have square tables, but mine does rectangular tables. Oh, and by the way, when you use my formula on a square table, you get the other values. So technically, there's really only one thing to worry about here. Okay, now this caused some trouble to you on the prep quiz. The visual representation. Okay, so these are the numeric values. I have a couple minutes. Okay, we came through measures of center. Numerically, mean, mode, median. Graphically, histogram or box and whisker plot. Okay, now you wouldn't want to make a histogram always works. Doesn't matter the type of data. And histograms could be either grouped or ungrouped. You don't want to have it ungrouped and have the values string out for a mile. You want them kind of grouped and ungrouped. And there's rules and guidelines in there. The software basically does that for you. You just have to figure out roughly how to do that. Shape, histogram, right? We see the shape with a histogram. Now you can make continuous lines called density plots. I don't have time to do that tonight. I'll show you that. It's not in the material, but it's good stuff to kind of know about. Time sequence. We didn't do anything with time sequence. Anytime the data that you collect is collected in, or the specimens were produced in a specific time sequence, you need to look at the time sequence. That's called a run chart or an individual's plot. It's in there. I didn't show it to you. There's some fancy stuff we can add to that. I'll do that later once we feel a little bit more comfortable. But you can reproduce all these things by checking. When we have, and for a time plot, a time representation, there is no numeric value to calculate. technically the orbit's way beyond the level of this course, so we just talk about just looking at the plot. Now we have relationships. The numeric value for relationship continuous is Pearson's R. Ordinal to ordinal is Spearman's rank order correlation, and nominal to nominal is Kramer's V. Now, what are the pictorial representations? Well, for continuous to continuous, the representation is a scatter plot, the pictorial representation. For ordinal to ordinal, you can also use a scatter plot, but sometimes they get looking pretty weird. But that's the best we have. For nominal to nominal, the pictorial representation is the physical scatter plot, is the physical contingency table with the frequencies in the cells. And in the content material it said you need to see this by making a table. And let me show you something really cool about the table command in R. The data that we have going here is what? Modules.voltage, voltage in the modules. Okay, so let me do this. I can make a table out of modules voltage. And you always have to spell things right.
Alert.
And what it will do is it will take the individual values in the data file and then count the frequency associated with them. So these are the values and these are the frequencies. So if I want the mode, when you looked at the mode, it said it is done by observation, not through a calculation. You look at the frequency, and you can do this with a histogram as well, an ungrouped histogram, and it will show you the same thing. Now, when you have data that is in X variable and Y variable, that's categories, category 1, 2, 3, category 1, 2, 3, and their various combinations. When you use the table command, as you will have seen here, based on energy, I can do this really quick. You can't, because import data set, local file. It was energy.
Energy.
Energy, okay. Notice it has two columns of data. It has a heading, and notice it identifies two columns down on the bottom panel. So I import that. I close that because I don't need it. And what am I doing? Oh. Cancel, modules, I want to close modules. Okay, I've got that. Okay, so now with that, I always want to do structure of this guy, which was energy. Oh, crap. Okay, it tells me that I have two integer values in there, and I can always look at the first bit of that file by typing the word head. I want to see the head of the file. And it will show me the first six lines. If I want to see the whole thing, then I just type energy. That's the whole file. So I have 1s and 2s and 3s and 1s and 0s, okay? So now, if I want a frequency representation of that, I use the table command. And I got to use the right one. I can't remember. I think I can just put just the data frame name in there. Yes, table energy. And I want to or GY, I want to display the result of that. So I just and so there's my table. So that is my pictorial representation of categorical to categorical data. Now, I can make a scatter plot of that, and the way you make a scatter plot is with the plot command, and I have to give it, I think if I just do energy, there's my scatter plot. See, I've got ones and ones, I've got twos and zeros. I got zeros and ones. I've got ones and ones. I've got zeros and twos. I've got zeros and threes. I've got ones and threes. I've got ones and twos. But it doesn't tell me how many. So scatter plot, when you start going down from continuous to ordinal to nominal, scatter plots don't look very good. And so we would use this as our pictorial representation for the relationship of categorical variable. Now to do the computations on those, they're in here. We would do Kramer's V, so up here we would do COR colon. And as soon as I do, it starts to auto-populate. I can scroll down to Kramer's V. And then it says you need the observed frequencies. The expected frequencies are calculated. I have to look this up. I've had my mind thinking about too many other crazy things. No, let's just do. Notice, if I press tab, it says observed frequencies. Then I can just tell it that I want the observed frequencies that are in the table or in energy, and it should be good to go. In the past, it used to put an X in there, and this gives you the output. There's the value. Right here is the value of Kramer's V. The other stuff in here we don't have to worry about for right now. That's not the same value. I got to make sure that didn't get updated over the summer. Put a big question mark on that. Okay, I've taken up enough of your life for tonight. All of our lessons or class discussions will be rather much like this. Do the binaries that you have. You have an assignment on this unit to do. Before you do that, I would suggest that you take the time, number one, to go read through the material again, and as you do, read the data files in, type the commands so that you get used to doing that. You can download and save your list of LOLCat functions if you want, and do the binaries that are due there. Instruction will be helpful, and we should be good. Next week, we're going to do Introduction to Probability.
Can you save the workspace on this?
Okay, now, if you want to save this stuff, right here, just click on File and Save As. So this will not save for me, but I'll just say second class, save. And it will save that. If I add something new, you'll notice that it turns red and it tells me that I need to save it, so I can just click on either of these two buttons and it will save that file, and it will save it in your default directory. Wherever you set up R, it will just save it there. On your own computers, it's fine to do it that way.
I can close it.
So when you get done, you can just save this again. Then when you click Exit, it says, do you want to save the workspace image? That will save all of the variables and the values off to the side. A lot of people that are more sophisticated say don't do that because you can always recreate it if you kept the code. But me, I keep it. I don't like to throw anything away. I'm just nervous that way. So I can say save it, and it's going to save it in my default directory where this is pointing to. Okay, say it. I can do this. You can do this. I know it's a little bit rough and awkward, but we don't do anything with R for the next week other than your homework assignments. Will give you a chance to kind of catch up. Then we'll be on a good path. So you're in. You can access the website. You took the honor code quiz. Okay, I need to see you, Diana, before you leave. Everybody else got taken care of in terms of getting their data files in? Okay, Jesse, thank you.
So by the way, due date on end of the month.
What's that?
Due date for the binary and
It's on the D12 website, in the calendar.
dates.
What's that?
Dates on the website is September, May.
Well, just